So, as we talked about here, we talked about material characteristics. Okay, so when we talk about material characteristics, you could have liquids, you could have solids, or you could have viscous materials. And the process of mixing in liquids, in solids, and in viscous applications is very different. See, primarily in liquids, we are able to generate flow currents. The moment you have an agitator getting into a liquid, and you can see in the image, as the agitator starts rotating, depending on the kind of the agitator, whether it is capable of generating an axial flow, that is the one on the right, where you can see, a top-bottom mixing pattern, or a radial flow, where you see that, the mixing starts radially. So depending on the kind of agitator, the agitator speed, you will have currents, flow currents generated, and you could have axial mixing, you could have radial mixing, and you can get, a truly homogeneous, well mixed product when it comes to liquids. Well, that's not the case when it comes to solids. Okay, and I'll just run a simulation of a B blender here, which is basically a gravity blender or a tumbling blender. So in case of solids, there are no flow currents. Therefore, the kind of perfect mixing that you get in liquids, you can't get that in solids. And the principle of mixing here is primarily, either you have a diffusion blending, or you have a convective blending, or you have a shear blending. Now, what diffusion means, what convective means, what shear means, we will discuss. Okay. And then when we're talking about viscous materials or dough-like materials, again things get very different. Now just imagine, taking a glass of water and putting in probably a flavored sugar syrup in that and stirring it. We get a homogeneous mix. Next, just think of adding some, mixing some spices together, powdered spices, and you get a solid mix. Certainly, it's not as good as a liquid mix. And now think of kneading dough. When we prepare the roti at home, okay, we prepare a dough which is basically solid with water, and we knead the dough. Now, that's an entirely different process, and what you need there is, a contribution of dispersive mixing and distributive. When you say distributive, you kind of, reorient. When you knead, you basically take the dough and you shape it in different directions, elongate it, turn it around, compress it. So you are basically distributing that, and you are also carrying out dispersive mixing, where the solids are well dispersed in the mass. So it's a combination of dispersive, distributive, and convective mixing, and you need lateral and transverse motion of material, and you need basically forced shear or elongation flow of the matrix. That's how viscous doughs are mixed. Okay. So we looked at the different characteristics of material. Okay, and we also need to look at the properties of material. So these were like solid, liquid, and viscous dough. And now when you take the ingredients may have a certain particle size, a particle size distribution. That's very, very common in the refractory industry. The density, the composition, the structure. We also look at bulk properties such as flowability, bulk density, segregation tendency, dustiness, rheology, deformation, and flow. As I said, there are properties such as material adhesiveness, material cohesiveness. When we talk about solids, you talk about the angle of repose. Particle shape. You could have some materials which are spherical in shape, some which are out of round, cubical, flaky, needle-like. So all of these factors need to be accounted when we are selecting a mixer. And when it comes to liquids, the density and viscosity of the liquid. These are the two primary characteristics of the properties that we look at. Are we going at a good pace? Can I have a
Yes, sir.
feedback?
Yes, sir.
Great, great. Fine,
Please
thank
go
you.
ahead.
I will continue. I will continue. So again, it's not that when we mix something, the mix is 100% uh, an ideal mixture. An ideal mixture, as you can see on the image at the right, you see a segregated material. So you have material A, which is in blue, and you have material B, which is in red, and they are completely segregated. And I try to mix them. You don't get an ideal mixture like you see in the second image where they are equally distributed. It is always a random mixture. Okay? And when you talk about, primarily when you talk about solids, we see more of random mixtures than really ideal mixtures. So we basically refer them to as structured and random blend structures. Let us understand what we mean by that. In structured blends, the different blend components interact with one another by physical, chemical, molecular means, or a combination of these resulting in agglomeration. The agglomerates thus comprise of uniform blend of smaller particles. So these are structured blends. When the different blending components do not adhere or bind to each other within the blender, that is when we say the structure is random. It's a random blend structure. Fine materials, and in definitely you use a lot of fine materials in refractories. They have a particular tendency to adhere only to themselves without adhering to the dissimilar components. Say, for example, you have carbon black or fumed silica. So in such cases, you need to adopt the mechanism of shear blending, to carry out the mixing. And no discussion on mixing can be completed without discussing segregation. Okay, so segregation and mixing are opposing processes. Segregation occurs during blending, transport, storage, or discharge. So you might have the best mixer, but if you don't handle the material after mixing, you might end up segregating what you mixed. So it is very important that the design of the system takes care of the fact that there is no segregation. Segregation happens more with the free flowing powders since they can separate easily, and the size, shape, and density when you are handling materials with different particle size distribution, different shapes, and different densities, that's where you experience segregation. How do you overcome segregation? Well, minimizing the physical differences, of the formulation, increasing cohesiveness. You may not be able to minimize physical differences. In that case, you need to find a way to increase cohesiveness of the formulation and optimizing the blending conditions. Okay, and as I said, it is not just limited to the blender. It could also be with your handling of material post blending. So all these need to be taken care of.